Hey everybody, today we're going to start on chapter 10. We're getting near the end of the semester, so maybe we can try something new and a little bit fun. So let's think about it, and we can see the end of the tunnel at this point. Okay, let's get started. We're going to talk about group homomorphisms, which we've already been talking about a lot, actually, except we were talking about the special case of a homomorphism, which is an isomorphism. A homomorphism is any map from a group to another one that is operation preserving. Okay, so it doesn't need to be one-to-one and onto, but if it is onto, then sometimes it's called a representation. We're not going to use that too much in here, but one thing we will talk about a lot is something called a kernel. Kernel of a homomorphism is any element in the domain that maps to the identity and the range. So let's see if there are any sort of useful examples that we can think of off the top of our heads. Maybe. Okay, so let's think. Maybe, how about, let's take a homomorphism that goes from the 2x2 matrices with entries in R and maps to the multiplicative real numbers. So that is the real numbers without zero using the operation of multiplication. So what's the kernel here? Oh, well, this is, sorry, what are we going to do? We're going to take a matrix that has a non-zero determinant, and the map is going to give us the determinant. We know the determinant is multiplicative, right? So it's definitely a homomorphism, right? The determinant of A times B is the determinant of A times the determinant of B. So what's the kernel here? Well, these are all the 2x2 matrices with entries in R that have determinant equal to 1, right? The special linear group. That would be an example of a homomorphism and its kernel. What about sort of obvious thing? You take a group and map it to, well, all right, I'm getting ahead of myself. So take the integers and send it into the integers modulo n. So obviously, we're going to take x and then send it to its equivalence class modulo n, right? So what's the kernel? It's all the multiples of n, right? But this, in general, is called sort of the canonical mapping from a group onto a group modulo some normal subgroup, where we take G and send it to its coset element in the factor group, where H is normal in G, right? So then that makes the kernel just equal to that normal subgroup. Turns out that the kernel of a homomorphism is always a normal subgroup. That we're going to talk about not in this, maybe not in this video, but a new video. But this is a fact. H is normal in G if phi is h for some homomorphism from G into some other group. Okay. Well, and it's an if and only if, right? So if it's the kernel of some homomorphism, then I can find this mapping here, and it's going to be a homomorphism with that being the kernel, right? So this is basically a really important fact we're going to use over and over again. All right. Now I'm going to have a little bit of fun. So now I'm going to talk about knot theory. This is one of the things that I do or have done in the past. So in case you don't know, what is a knot? Mathematical knot is I didn't draw that very well. It's a circle that lives inside three-dimensional space. So here's an example of one. Okay, so this is a diagram or a picture, two-dimensional picture of something three-dimensional. So a knot is, K is really a circle or loop that is inside three space. And we think of them up to something called ambient isotopy. Think of the knot as actually being a shoelace that you tie in a knot and then fuse the ends together. But it's really bendy and really stretchy. You can bend it and stretch it and turn it and do whatever you want to it, so long as it whatever you're doing is allowed in the three-dimensional space that it lives inside. So, like, if I look at a diagram here, turns out this is a fact. Two knots are the same up to this equivalence if and only if there are two-dimensional representations called diagrams are related by a finite sequence of the following moves that are, these are local moves. So they're called Reidemeister moves. So the first one is, well, say you have any piece of the diagram looks like this. Well, I can add a twist if I want, right? So if it's bendy, I can pull this piece up and give it a twist, either right-hand twist or left-hand twist, doesn't matter. This is a twist, okay? Essentially, I didn't say this. Ambient isotopy means I can move these strings around, but I cannot cut them or put one through the other, right? It's like a physical piece of rope. Okay, so these Reidemeister moves are going to be a diagrammatic way to relate. two knots. I mean, it's really hard to decide when two knots are the same, right? Just because you don't know how to make one diagram look like the other one by these moves doesn't mean that such a sequence doesn't exist. So we're going to see that there's better mathematical ways to do this. All right. Another one is if you have two parallel bits of diagram, you can put one over the other one, or you can pull one under the other one. Either way, that you can go backwards or forwards, something like that. So if you have an overcrossing and another overcrossing, you can undo it, or you can add that. Okay. And the last one is if I have a crossing and I have some other arc that goes over it, right? I can pull this piece way over the top of that crossing. Okay. All these things seem quite natural if you think about what you're actually doing and if you were thinking of these things as ropes. Okay. But once again, just because I don't know a way to make one diagram into the other one doesn't mean that such a sequence does not exist. Okay, so we're going to develop some other way to show two things are different. Now, it looks pretty clear that this thing is different than this thing, right? So the unknotted circle is different than that one, right? So these are examples, right? Example 1, K1, this is K2. Okay. Well, it's not quite obvious, I guess, or not rigorous to say, well, this one has 3 crossings, this one has no crossings. Maybe there's some crazy way that I could use Reidemeister moves to undo the crossings of this second one here. Well, we're going to find a really fast and rigorous way to show that that's never possible by using something called a invariant of knots that uses a homomorphism. So first things first, okay, there is a group that is associated to a knot. That is invariant under Reidemeister moves. Okay, well, I should say it's associated to a diagram of a knot. And so if it's invariant under those Reidemeister moves, then we say that it is an invariant of the knot type. Okay, so if you have two knots that are different under ambient isotopy, they cannot have, or they might have the same group here, but if they have different group called the fundamental group, we know that they are not the same. All right, so a knot invariance like a function from the equivalence classes of knots that's well defined. Okay, so in other words, this group is called fundamental group. Of the knot exterior. Oops. Take R3 and take away the knot. All right. We can denoted by pi1 of the knot K. What is this thing actually? Well, let me try to give it to you in as an example. So the elements of this group are loops so other circles that exist in the ambient space around the knot that are equivalent up to, and there's a multiplication, right, given by, so follow the leader, right, you do one, then you do the other one. So they're actually, the elements are ordered loops, right, so elements in pi1, so let's take L, right, pi1 of K. Right, L is actually an ordered or oriented path in the exterior of the knot, so that L of 0 is equal to L of 1. So it starts and stops in the same place. And I'm going to call that place x0. So x0 lives out here somewhere at some point. Okay? And L goes out there. You can represent it by some curve with an arrow. Let's say it goes through there, right? Comes back out, does something crazy. Who knows, maybe it does something like this itself, but it comes back to here. Okay, so this is L. Now, the equivalence relation between, so these are a set of equivalence classes. And two loops inside pi1 are the same if when you take one and then the other one in reverse, they bound a disk. So no holes in there. So we say L1 is equal to L2, under this equivalence relation. If L1, L2 inverse is the boundary of a two-dimensional disk. So here's an example of two, and one could say that one can be continuously deformed to the other one. So for example, here's the base point, right? Here's L1 maybe, okay? And then here's L2. L2 is here, right, going around in the sort of same direction. Well, if I look at L1 and then L2 inverse, L2 inverse is going around in the opposite direction, right? So if this has order, right, the inverse just goes around the loop backwards. So let's look at what L1, L2 inverse looks like. So go L1 around, and then we go, oops, go around L2 inverse. Okay, and what we get is really weird looking, but that is a two-dimensional disk with no holes inside. Okay, so maybe I've told you more than you need to know, but here's the thing. I want to find this knot group is very, very complicated, right? But if I can find a homomorphism from the knot group onto some well-known group, okay, and that's possible for one knot but not possible for the other one, then we know that those two knots can't be the same. So it turns out that this is true if we think about taking elements from the loop and assigning to them, or loops that are in pi 1 here, and assigning to them elements of the dihedral group. Such things called a coloring. We can take some alpha in the fundamental group of the knot, okay, and assign to it an element of, let's say, D3, okay? If we can find a surjective representation, so there's always one that's trivial, right? But if there's so this symbol means onto. If there's such a map, that's a homomorphism and onto. Then we say that K is quote-unquote three-colorable. Now, without getting too technical, the way this works is, it turns out that every element, this was proven by a guy named Verdinger. How do you spell his name? Remember if it's, how do you spell Verdinger? I don't know. Vertinger. That doesn't look right. Okay, forget it. Someone's rolling around in their grave. Anyway, in fact, there is a generating set. Every element in the fundamental group and D is a diagram for K. Then alpha is of the form well, it's of the form equals some sequence of elements x1 through xn, powers of elements x1 through xn, each of which correspond the arcs of the diagram with some relations, right? So, for instance, in the case of trefoil, right, there are three arcs, x1, x2, x3, and so base points out here, x0, right? Every loop, so let's put an orientation on the knot. It's not necessary to do this, but I want you to sort of figure out what's left and right, anyway. So if you think about a loop as starting from here, right, does some straight line arc sort of near to where this diagram is, and remember the knot is removed, right? So now I want to go to this little guy here that goes from right to left of there. That would be, so it goes to this thing here, travels underneath there, then back up straight to the base point. So that was going to be my loop there. I have another one. I don't know. So this little arc here, this little guy here, means I have another loop that's turns out to be a generator. Goes from the base point down to that little arrow underneath the arc of the diagram, back up again. Let's find another pink. Okay. Goes straight down there, bang, hits that one, goes back up. Right? Those are all generators of the fundamental group. Okay. Now, we can then define, so pi 1 of k is generated by these three letters with relations. Okay, I'm not going to go there, right? I haven't gone over the generators and relations section yet, but basically this means that everything in this group is a sequence of these three symbols with their powers, positive and negative powers. And then there are some rules here as to how I can sort of make those words equivalent to one another, right? That has to do with there are relations that correspond in this case to each crossing, but we don't need to worry about that. Here, I take this thing and I'm going to map it to D3 if possible by assigning colors of the diagram. So I've used red, I've used green and blue and pink, right? So that can be, so remember this thing is of the form R and S, with R to the 3 is a relation, because that's rotation. S squared is the identity, and then oops, some more space. Okay. Let me go to the next thing here. Okay. So I'm going to define something here. This is going to be R and S, such that R cubed is the identity. S squared is the identity, and RS squared is the identity. Okay? That's one way to think of the dihedral group. Okay. I've already given you the way to write the formula for this homomorphism. So we take the coloring, takes a knot, right, assigns it to something on, in this case it's a 3 coloring, a 3. We're going to take the arcs of the diagram, we're going to color them with 3 colors, 0, 1, and 2. Okay, so like x1 goes to RS to the 0. So that's green. Okay, x2 is going to map to RS to the 1. That's pink. Oh. My pink, here it is. RS to the 1. And x3 is going to be red. RS to the 2. Okay. Why is this on 2? Well, first of all, why is it a homomorphism? The hardest part there is showing that it is well defined. It turns out that those relations work out with this, and it is operation preserving. if at every crossing, so this works, only when the colors are assigned to the diagram, colors say 0, 1, and 2, are assigned so that at every crossing there is either all the same color or all different colors. Either we have all the same crossing, A, say all those are green maybe, or at a crossing we have all different. Oh, that's not working. Okay. 0, 1, 2. So either we have all the same color, right? Or all different. And we need at least one crossing that has all the different ones, or we don't get a surjection. Okay. Why is this onto? Well, it turns out that if you have all of these guys, right, RS0 is a generator, right? That's R, so R is in there, and RS is in there. Wait a minute. Oh, sorry, this is wrong. It's supposed to be R to the 0S. Oh, shoot. Did these wrong. So everything in here, sorry, S is the reflection, right? So R to the 0S, R to the 1S, R to the 2S, right? So you have S and you have R1S. Take the Y onto, I guess I should say. Well, we know that S is in the range, right? And we know that RS is in there. But we also, all we need is just R, right? And we know that in this case, the element x2, x1 will map to R. So maps to RSS, which is R, right? So we have definitely all the generators are in the range, so we know it's onto. Why is it operating restriction? Well, it is if we have this. And so what's the upshot? Well, this knot called the trefoil I can't draw it. I'll sudden. There we go. This is not the same as this, since here we can only add one color. Here we can have all colors, 0, 1, and 2. Right? So this thing here is 3 colorable. But this one is not, right? So we don't have a onto homomorphism from the knot group of this, which turns out to be Z, by the way, the integers. So it's a pretty straightforward thing, right? Go around this loop once, that like is isomorphic to 1, and then go around it twice, 2, and so on and so forth. Anyway, shows that these two things are different. Okay, maybe I spent too much time on that. All right, back to what we need to say. We're going to do one thing, so I'm not wasting all your time, I guess. Let's prove this homomorphism, or this proposition, right quick. How do you prove that a homomorphism is one-to-one? Well, that's true if and only if the kernel is trivial. In other words, the kernel is equal to the identity only. Right? We know that the kernel phi is non-empty, since any homomorphism is going to map the identity to itself. So we know that the identity is in there, right? Okay, how do we show, but we know that that's it. We know that that's in there. To show that it's trivial is to say that the kernel only has the identity. So to say that the kernel is trivial, what we mean that the kernel is just the identity. Okay? So let's go this way first. So say phi is 1-to-1. Okay? That means that if phi of x equals phi of y, that's x equals y. Hence, if phi of x equals the identity, right, and that means that phi of x times phi of x inverse equals the identity as well. Well, that also equals hold on a second. Yeah, let's just say it this way. 5x equals the identity, and 5y equal the identity. That means that x equals y, right? And they must all equal the identity. Okay, there's not really much going that way, right? What about the other direction? This is the one that's less obvious. So say those two things are equal, and that means I can multiply both sides by the inverse. Okay, that's the identity. But phi is a homomorphism, so does operation preserving, right? So that means okay. So this, in other words, xy inverse is in the kernel, but the kernel is trivial, which means they must be equal. So therefore, phi is 1 to 1. Okay, so I hope this was, I don't know, food for thought, but I'll get more into the meat of this section next time. I just kind of wanted to play around a little bit. So I hope you had a good time. Put any questions or comments about the material in the the discussion forums that are made for that. Okay, bye-bye.